In this chapter, we're moving on to capacitance. So from this chapter onwards, there's going to be a lot of talk about applications of electricity and magnetism to life and medical physics. But of course, at the beginning, we still have to go through an overview of what capacitance is, what are the important equations, and do a few sample problems. So what are we going to talk about in this lecture? First, we're going to go through a recap of the important concepts from conductors and dielectrics, especially dielectrics because we're going to have to use them for capacitors as well. Then we're going to take a look at capacitors and capacitance, as well as what happens when you connect capacitors in series or parallel. Do a little bit of a summary and a recap about dielectrics and how they're useful in capacitors, and then take a look at energy storage in capacitors. Now, once we have a good overview of all of these different topics, we're going to move on to applications. So we can talk about biophysical modeling through, let's say, assuming that the two layers of the cell membrane are parallel plate capacitors. We can take a look at biosensing and touch screens. So anytime you use your mobile device and you're touching the screen, that is also considered some sort of capacitance between your finger and the device itself. And of course, for medical physics, we're going to be taking a look at defibrillators, which use capacitors to store a lot of energy to deliver electrical shocks. Okay, so let's start off with a review of conductors. So conductors, I think, was pretty fun because we got to draw different diagrams and also take a look at the electric field distributions around charged objects, and also look at the charge distributions. So I basically have 2 to 3 slides here summarizing everything. First of all, we learned that when we're talking about dielectrics, in which case a dielectric is an insulator that can be essentially polarized and have an induced charge either on the outside or the inside. So a polarized dielectric will have dipoles throughout the material like this. So when we're talking about dielectrics, we also use a different form of Gauss law. It has the displacement vector d in it, which basically means how much has the polarization affected the electric field. Then you have an updated version or a slightly modified version of Gauss law where you include this displacement vector. So that makes sense because when an object is polarized because of an electric field, it means that it would probably be displaced in some sort of way through its electric field distribution. And so we use that new version of the electric field to calculate total flux through Gauss law. The other thing to keep in mind is that when you're using Gauss law for dielectrics, you have Q free, which is no longer Q enclosed over epsilon naught. The epsilon naught has now been included in the equation for a displacement vector. So those are the 2 main changes when you're talking about dielectrics and Gauss law. Introduction of the displacement vector, which includes epsilon naught, and therefore we do not need epsilon naught on the right side of the equation. Okay, next we talked about properties of conductors in electric fields. So the 5 main properties: the electric field is always 0 inside a conductor, that's always given. The charge density is 0 inside a conductor, also true. A conductor is an equipotential, so keep in mind, if a conductor is an equipotential, it means any charge that resides in the conductor will automatically move to the surface, and that leads us to number 4. Because the inside of the conductor has to have a charge density of 0, it means that any charge that resides within the conductor will have to move to the outer surface. So when we were doing questions about conductors with a hollow core and an exterior surface, so there would be an inner and outer surface. If you release a charge on the inner surface, it's still part of the conductor itself, and all net charge is going to reside on the outermost surface. And of course, because a conductor is an equipotential, the electric field is going to be perpendicular to the surface just outside a conductor because the net charge resides on the exterior surface, or the outermost surface of the conductor. In the previous chapter, we went through a bunch of examples with conductors and what happens when we introduce a positive charge close to it or inside a hollowed out sphere like this. So in this case, we have essentially two conducting shells. The first shell is over here and it's empty, and the second shell does have some sort of conducting substance inside it. So we would call this a conducting shell. Now we have an inner surface and we have an outer surface over here. So in this example, I'm just going to walk through a review of what happens when you introduce a charge on one side and what happens if you ground one of the surfaces. So I'm going to switch to the pen. I'm going to introduce a negative Q charge over here. Ooh. Let's just assume this is minus Q. So if I have a negative Q charge over here, it means that it's going to attract a bunch of positive charges from this neutral conductor. And the other thing to mention is that if we just simply say conductor and there's no net charge on it, just assume that it starts off neutral. Okay, now we have a bunch of negative charges here. So there is an uneven charge distribution. The positive charges will want to go towards the left to be attracted to the negative Q, and the negative charges are going to be on the right because they'll be repelled by the negative Q. So that makes sense. Now, what happens if we ground the conductor? So this means I'm going to ground the right side. So when I ground something, the first thing we should understand is that the potential of the conductor will want to go to zero. Now, the only possible way of doing this is by providing enough charge, whether it's providing more negative charge or taking away negative charge to make it positive, to allow the charge that has built up on the side to be neutralized. So if I'm taking a look at this, this is a very negative charge on the right side, but the positive charges are still attracted to the left side. So that means when we're grounding the right side of the conductor, the only thing that's possible is for our negative charges to go into the ground. Oops. Let's just... Okay, so those are our negative charges. They go into the ground, and essentially the right side is neutralized and you achieve a potential of zero. However, what happens after you remove the ground? So when you remove the ground, there is the assumption that the charges will be redistributed around the entire conductor surface, but that isn't true in this case because of the presence of a negative Q charge on the left side. No matter what, if you remove this ground on the right, then the ground has effectively removed all of the negative charge over here. So overall, you have a net positive charge on your conductor. And for the net positive charge, you will always have that shift in charge distribution where there will be more positive, the left side will be more positive than the right side because of the presence of the negative Q charge on the left. So that's just an overview of conductors, what happens after grounding. Think about charging by induction when you're looking at grounding effects, and what happens afterwards. Now let's move on to electrostatic energy and capacitors. So basically, what are capacitors? What's the big picture we're looking at here? And then why are capacitors important? So for the big picture, we already learned about electrostatic energy, but what we didn't discuss is how electrostatic energy can be stored in different configurations of electric charge. The way we can do that is through a capacitor. That's a device that can store electrostatic energy. It doesn't just store it, it can also charge it. So capacitance will basically be a measure of how much that capacitor can store. So the actual definition of capacitance is the ratio of the change in electric charge in a system to the corresponding change in its electric potential. So you can also correlate this to the effect of a capacitor. So when were they first discovered? The earliest forms of capacitors were actually created in the 1740s. European scientists discovered that Leyden jars, something that looks like this, could store electric charge. Essentially, it's a glass jar with water. So take a look into that if you're interested in the history of of capacitors, but it all started with Leyden jars. Why are capacitors important? Capacitors are essential to modern technology. What they do is they help store little bits of information in PC memory. We all use them. They provide a steady current to your stereo amplifier. They also help store high bursts of electric energy for fuel cell and hybrid vehicles. So there are many different applications for capacitors, and they're very, very important. Not just that, we are going to focus on the application of capacitors to life and medical physics. So touchscreens and small electronic devices, they all use capacitors, especially when you're doing biosensing. Next, you're taking a look at defibrillators and other medical devices, where we can take a look at cell membrane modeling, where you have one layer of the cell membrane and another layer, and it looks like a parallel plate capacitor, which we'll talk about in the next chapters. Let's move on to capacitors and capacitance. So now we actually get to try and quantify capacitance to see how much electrostatic energy or capacitance a capacitor can hold. But first, we have to understand what a capacitor is made of. And a capacitor really is made when two conductors are separated by an insulator or a vacuum. So in this example, we have a conductor on the bottom and a conductor on the top, labeled A and B respectively. And in between, in this case, we just have free space or vacuum that's separating the two conductors. So each conductor has zero net charge initially, but when you're charging a conductor, it means that you're transferring electrons from one conductor to another. So let's define that further. I'm now going to take a look at a parallel plate capacitor, and that's the easiest example to give because capacitors can come in many different configurations. So for a parallel plate capacitor, it consists of two closely spaced conducting plates. You have a top plate and a bottom plate. In this case, it's got a positive charge on the top plate and a negative charge on the bottom plate. And each plate has a specific surface area, A. So the simplest form of a capacitor is with two parallel plates, each with area A separated by a distance D. One plate holds a positive charge and the other holds a negative charge, and you end up being able to find a potential difference between the two plates. So we can charge a capacitor by connecting the two wires, here and here, to opposite terminals of a battery. And that is how this potential difference is created. So without this wire and without the connection to the different terminals of a battery, you will not get that potential difference that you're looking for. So if we're talking about charging a capacitor, we can think of connecting these two wires, and once the positive and negative charges are established on the conductors, we can disconnect the battery. Now this will give us a fixed potential, VAB, between the conductors that is equal to the voltage of the battery. So when we were talking about grounding before, apply the same concept over here. We can charge a capacitor and then take away the battery. And it'll still retain a fixed potential difference between the two plates. Now, when we're taking a look at parallel plate capacitors, we also have to take a look at what happens to the electric field and what the electric field distribution looks like. So the charge on the plates is going to create an electric field between them. So there's going to be a uniform region of electric field between the two plates, which makes sense because the top, in this example, the top plate is positively charged and the bottom plate is negatively charged. So the positive, the electric field lines are going to go from the positive to the negative, so they go straight down. Now, on the very edges of the parallel plate capacitor, that's where things start to look different. Because the parallel plate capacitor does not have an infinite plane, it means that on the very edges of the parallel plate capacitor, you get these curved electric field lines. They won't just go straight down. And these are what we call fringe effects or fringing. Now, when we're talking about fringing, if we move the parallel plates closer and closer together, or essentially if we reduce the separation distance, then the effect of fringing will not be as significant as if you had those plates farther apart, because the value of fringing will be smaller. So it says over here, when the separation of the plates is small compared to their size, the fringing of the field is slight. Now, why is that? It's because the closer and closer you bring these two parallel plates together, the more it'll look like an infinite plane to a point that is in between those two plates. So that is why the fringing field is going to be reduced as the separation distance is decreased. Now, how do we represent capacitors? We are going to be taking a look at circuits eventually. So in circuit diagrams, we represent capacitors with either of these two symbols. Commonly, we just use this. Now, next, we do want to be able to determine capacitance mathematically. So we don't just want to be able to label circuit diagrams. We need to be able to differentiate between different capacitor systems and figure out how to calculate capacitance. So when we're taking a look at capacitors, we're going to use capacitance to measure some component of a capacitor. So if we are able to connect the electric field of a capacitor to the potential difference, we then are able to introduce a term called capacitance to give us a way to quantify the electric field and potential difference of a capacitor. So now that we understand what capacitance is, it would be good to be able to derive an equation for capacitance so that we can actually quantify this. So the parallel plate capacitor is made up of two conductors. And one thing to remember from Gauss' law is that the field at a conductor surface is given by this equation over here. E is equal to sigma, or surface charge density, over epsilon naught. So keeping that in mind, we move on. And we ask ourselves, what about the surface charge density for a parallel plate capacitor? So if we have a parallel plate capacitor, we still have conductors. And if the charge is Q on a plate with an area A, then the surface charge density is sigma equals to Q over A. So that should be fairly intuitive to think about. After you have that, we can write our equation for the electric field. It's going to be E equals to Q over epsilon naught times A for a conductor. And now we have to tie this to potential difference V. We know that the potential difference is defined as delta V equals to the negative integral from A to B of E dr. Since the electric field is constant in both directions, we can really simplify this equation so that we have V equals to E times D. So that makes sense. Try the dot product over here with E dotted with dr. If the electric field is constant in both the directions, you can factor out the E, and then you just have the negative integral of dr, which is the distance or the path traveled. And so you end up with ED as your final value. So we have an equation for E and we have an equation for V. So we can try and manipulate these two equations to see if we can come up with a new one. So we have E and V. We can rearrange V equals ED to E equals V over D, and now we can equate the two sides. So equating the two sides, you have Q over epsilon naught A is equal to V over D. If we want to be able to rearrange this again, we can have Q over V, like this, is equal to epsilon naught A over D. So this was simply where I moved the Q over here and I moved epsilon naught A to the right side. So it's epsilon naught A times V over D, but we did want to try and come up with a term for capacitance. So we define capacitance as some charge over some potential. And that gives us epsilon naught A over D, and it leads us to the equation for capacitance that we're all familiar with, which is epsilon naught A over D. So in this case, there are two ways of defining capacitance. If we know the setup of the capacitor system, then we can use this equation because we'll know the separation distance, we'll know the area of the of the plates or the conductors. If we have a circuit and we're looking at charge and potential difference, if those values are given to us, we can just say capacitance is equal to the charge over the potential. So keep in mind that this only applies to the setup that we've created, which was a parallel plate capacitor. Other configurations will have different values of capacitance, and we are going to go through some of those examples. And by configurations, I mean whether you have parallel plate capacitors in series or in parallel. But even if we can calculate capacitance, we need to know what units to use. Now, for units, we know that it's Q over V, so it has to be charge or coulombs over potential or volts. So we know that the units for capacitance are coulombs over volts. But Michael Faraday, who's the one over here, in honor of this 19th century scientist, we simplify this unit to farads, or F. So we know the equation for capacitance, we know what units to use. Let's go through a few different sample calculations so that we can practice using these equations. Okay, so in this problem, we're taking a look at VCR memory. So when we're taking a look at video cassette recorders, they do have memory capacitors. And so that memory capacitor has a capacitance of 4.0 farads and is charged to 3.5 volts. The question's asking, what is the charge on its plates? So our goal is really just to see what kind of equation we have to use. So we're going to first state the known values, find the proper equation, and then solve for it. So what are the known values? The known values are going to be C is equal to 4.0 farads. We also know that the potential is 3.5 volts. It's asking us to calculate the charge. So the equation to use would most likely be C equals to Q over V, and then we can rearrange to solve. We have Q equals to CV, which is equal to 4.0 farads over 3.5 volts, and that gives us 14.0 coulomb as our answer. In problem 2, we're taking a look at the area of a plate. A parallel plate capacitor has a 1.1 millimeter plate spacing, and it has plus or minus 2.3 microcoulombs on its plates when charged to 150 volts. What is the area of the plate? Once again, write down your known values, find the proper equation to use, and then solve. So our known values are going to be D is equal to 1.1 millimeters, which is equal to 0.0011 meters. We have V being equal to 150 volts, and then we have Q being equal to 2.3 microcoulombs, or 2.3 times 10 to the negative 6 coulombs. Now, what kind of equation applies all of these? It's going to be our definition of capacitance, which is epsilon naught A over D, which is also equal to Q over V. Now, we're trying to find A, so it makes sense that we're going to have to rearrange for A. So A is going to be equal to QD over V epsilon naught. After that, we can just solve for area. Put sol over here. we have A is equal to 2.3 times 10 to the negative 6 coulombs, 0.0011 meters, over epsilon naught, which is a known value, a known constant, 8.85, times 10 to the negative 12 coulomb squared per meter, squared Newton. And then we have 150 volts for V. Just kind of reverse the two of them, but that's okay. Now, all in all, punch it into the calculator, we get 1.9, 0.583841 meters squared. Now, not too worried about this in this course, but there are significant figures. So why don't we just do 1.91 meters squared. I don't worry too much about it. Okay, and that's it for problem 2. Okay, in this problem, we're taking a look at different capacitances. So a parallel plate capacitor system isn't the only system that can be out there. There can be various different shapes. So in this one, we're taking a look at a capacitor that consists of 2 long concentric metal cylinders. So think of it as a rolled capacitor. Find an expression for its capacitance in terms of the dimensions given. L for the length of the cylinder, A for the radius of the inner cylinder, and B for the radius of the outer cylinder. So to keep things simple, we're going to draw a diagram first. We know that I'm just going to draw a really short cylinder, and there is a purpose for that. So I have my cylinder here, but I also have an inner cylinder, or inner surface to the cylinder. This is going to be A, and then this is going to be B. And there is going to be a length L. And there is line symmetry to this, so there's going to be, we can use the electric field for line symmetry. So next, we want to be able to evaluate the symmetry of the shape that we have and figure out what we need. So our goal is to find C. And we know that C is equal to Q over V. So that means we're going to have to first find Q. So let's have find Q, and we also will have to find V. So let's start off with finding V. Finding Q will be simple afterwards. For V, we know that the potential difference, between A and B is V. So that means we can use V equals to negative integral A to B of E dotted with dr. The other thing we know is that this thing exhibits line symmetry, and we already know that E is equal to lambda over 2 pi epsilon naught r hat. So that means we have V being equal to negative integral A to B of lambda over 2 pi epsilon naught r dr. We can factor out the constants over here, and we end up with B equals to negative lambda over 2 pi epsilon naught, and we end up with the integral from a to b of dr over r, which is just ln of r. So now we have negative lambda over 2 pi epsilon naught ln of b over a. But because of the negative here, actually, let's just keep it like this because it'll be simpler afterwards. Okay, so we have V, but we're not done yet. This is for the inner cylinder. What about the outer one? We must find delta V. So that's going to be equal to V out minus V in. For the outer one, the outer cylinder does not contribute to potential between the two surfaces. So I have to write that down. And that makes sense because if you're taking a look at the potential between the two surfaces of the cylinder, the exterior one really doesn't contribute because we're looking at the potential in between, not at the edge. So that means we simply have V out equals to 0. So that means your delta V would be equal to negative of the V that we just created, because this is V in. So that would be lambda over 2 pi epsilon naught ln of B over A. So that's our equation for V. Now we have to figure out what Q is. And because we know there is a charge density lambda given here, we know Q, we know Q is going to be equal to lambda times some sort of length L. So then we simply have our last step being solve for C. For C, we're going to get C equals to Q over V. Q is lambda L over, and then we have lambda over 2 pi epsilon naught ln of B over A, and that gives us 2 pi epsilon naught L divided by ln of B over A. And that would be our answer for capacitance for this problem. Okay, so we're now going to talk about what happens when we connect capacitors together. So these are the different configurations that I'm talking about. Now, when we look at capacitors, this is what they look like in real life. So there's various sizes of capacitors. When you go to the store, you can purchase capacitors of standard capacitances. So it'll actually be labeled on the capacitor itself what kind of capacitance it has. So what happens if none of them offer the capacitance you want? Because you can only manufacture so many capacitors of so many different capacitances. In such a case, you're going to have to start combining capacitors to achieve the capacitance you want. So we can then combine capacitors in parallel or in series to create equivalent capacitances. So capacitors in parallel and capacitors in series, they will have different equations, and keep in mind you will not have to derive the equations in this course. I will be presenting the derivations, but you will just need to know the final equations to use. So capacitors in parallel have the following features. A conducting wire is going to connect the top plates of each capacitor together. So you have two of them side by side, and a wire is going to connect the two of them from the top. Also, from the bottom, you have the two wires connecting the bottom two plates. So the top and the bottom of the plates are going to have the same potential. Each capacitor will also have the same potential difference because the top and the bottom are still connected to the different ends of the terminal of the battery. So when you're talking about parallel capacitors, you get parallel capacitance, which is C1 plus C2 equals to a summation of all of the capacitances that are connected in parallel. Now, let's take a look at what is required to derive this equation. So we already know that C is equal to Q over V, and in parallel, two capacitors will share a common potential or voltage. So that means Q1 equals to C1V and Q2 equals to C2V. So V is the same for both. Now, if we wanted to add up the charges, we would get the total charge is equal to C1V1 plus C2V2. So if we have the total charge, we know that we can calculate capacitance because capacitance is Q over V. And so the total capacitance is the total charge over potential. We know potential is the same. So it's just Q total divided by V. And that means we just remove V from each of these and we get C1 plus C2. So that is how we would derive the parallel equation for parallel capacitance. So capacitors in parallel, now we want to take a look at what happens when we draw this out in a circuit diagram. So in parallel, the capacitors have the same potential. Like I said before, the two top plates are connected by the same wire, which are both connected to the same terminal from a battery. And the bottom two plates are connected by the same wire to the other end of the battery. So that means the same amount of potential is provided to each of these capacitors. Now, these two can be combined. So when you're drawing a circuit diagram, which is something that you will have to be familiar with, you start off with this diagram and you try to simplify it each step of the way. So these two can be combined through the parallel capacitance equation into one equivalent capacitance presented by this. So you've now narrowed it down, or you've combined it into one capacitor with CEQ, which means equivalent capacitance. So next, we talk about what happens if capacitors are connected in series. So if you're connecting capacitors in series, they're going to have the following features. So there's no more connecting of the conducting wires at either end. They're just strung along in series. This means the voltages are most likely going to be different. And each capacitor is going to carry the same charge because the same amount of charge will flow through the capacitor from one end to the other. So think about if you start off with one end of the terminal of the battery, and then you have one line going to the other end, and you add in a bunch of capacitors along that line. You'll note that the same charge is going to flow through all of the capacitors, which means that the charge will be the same because it's carried throughout, but the voltages can be different for the different capacitors. Oops, don't want to go that fast. So the equation for series capacitance is 1 over the series capacitance is equal to 1 over C1 plus 1 over C2. So you're just summing up all of the reciprocals of capacitance together to get the reciprocal of capacitance in series. So in terms of this, how can we get this equation? We'll derive it. We already know that C equals to Q over V, and in series, they're going to share Q. So unlike how we derived the parallel equation, we're now keeping Q constant. So that means V1 equals to Q over C1, and V2 equals to Q over C2. Now we can add these two up to get the total potential. So we get V total equals to Q times 1 over C1 plus 1 over C2. And then from that, we know that capacitance is equal to Q over V. Q is the same, but V is now a V total. So we put that in the denominator. So C total is going to be equal to Q over, so the Q gets canceled out, and you get 1 over 1 over C1 plus 1 over C2. So you just move that around and you get something that looks prettier. You get 1 over C total equals to 1 over C1 plus 1 over C2. So that's the equation for equivalent capacitance for capacitors in series. So when you're drawing circuit diagrams, once again, I'm going to explain this visually and graphically. Pretend this is A and B are the two terminals of the battery. We start at A. There's going to be a charge, Q, that flows through this capacitor and then through this capacitor. So the same amount of charge is going to go through each of these capacitors. So that means Q stays the same. But the potential, because they are different capacitors, the potential can be different. So based on this, after we've applied our equation for equivalent capacitance in series, we can redraw the circuit diagram and turn it into one capacitor with CEQ equal to Q over V, or 1 over CEQ equals to the equation for equivalent capacitance in series. So what am I referring to when I talk about equivalent capacitance? It's the process of essentially dumbing down a circuit diagram so that if you have multiple capacitors in different configurations, you eventually end up with one capacitor. So you can always combine a complex network of capacitors to, so we start off here called the complex network. We have C1, C2, and C3. The first thing you want to do is take a look at all of the parallel capacitors. So if you have capacitors in parallel, reduce them to their equivalent capacitances. And then you take a look at whether there are any capacitors in series. If they are in series, then you apply the equation again for capacitors in series, and then you can reduce this to one capacitance. So you've simplified the complex network of capacitors into one total equivalent capacitance. Now, when I'm talking about circuit diagrams like this, it's very important that if you are asked questions like this on a test or an exam or an assignment, that you show all of your steps. So it should show steps from reducing parallel plate capacitors and then series capacitors to a single equivalent capacitor. So there are a minimum of 3 steps involved for this. Okay, so in this problem, we're taking a look at capacitor in series and in parallel. So we're given some sort of circuit on the right, and we're trying to figure out the equivalent capacitance measured between A and B in that figure. So remember the steps. Start with parallel, then go to series, and then go to the final equivalent capacitance. So that's exactly what we're going to try and do. So step 1, we're going to first label and simplify parallel capacitors. Why don't we label them first? So we're going to label this C1, and then we have C2, C3, and then C4. Just for simplicity. We take a look at which capacitors are in parallel. We know that C2 and C3 are for sure in parallel because they share the same wire on the top and bottom. So we end up with C2 and C3 are in parallel. And we know that the equivalent capacitance of parallel capacitors is just going to be the summation of the two of them. So we know C 2,3, which is C2 plus C3, is simply going to be 2.0 microfarads plus 1.0 microfarads, which is equal to 3.0 mu f. Okay, so that's the equivalent capacitance for 2 and 3. We're going to redraw this so that we have an updated circuit diagram, A. We have C1 over here. We have our C23, and then we have C4, and then it goes to B. Now, step 2, we're going to try and simplify this, and everything is now going to be in series. So 2, label and simplify, series capacitors. We now know that all three of these are in series. So C1, C23, oops. Let's just delete this. And C4 are all in series. So if we want to find the equivalent capacitance, CEQ, which is the final version, then it's going to be equal to 1 over C1 plus 1 over C23 plus 1 over C4. I'm going to move on to the next slide and just make sure that we have enough space to work on this. Oh, there's no next slide. Keep forgetting that. Okay. So over here, we then have I'm just going to do it here. CEQ is going to be equal to, we'll try to simplify this as much as I can with common denominators. So with common denominators, what we'll end up with at the bottom is C1, C23, and C4. So in this case, you can end up with 1 over C23, C4, plus C1, C4, plus C1, C23, divided by C1, C23, C4. So if we reverse this, we end up with C1, C23, C4 divided by C23, C4 plus C1, C4 plus C1, C23. And then we just have to plug in our values, and we get 3, 3, 2. At the bottom, it's a little bit more complicated. We end up with 3, and then 4 is 2, plus 3, 2, plus 3, and 3. And so CEQ is going to give us 18.0 over 21.0 microfarads, and CEQ is going to be equal to 0.857 microfarads. So that is the answer to the question. And as you can see, for each of these, just make sure you break down the steps that you've used to achieve the equivalent capacitance. So we finally come back to dielectrics, and in this subchapter, we're going to be talking about how dielectrics play a role in capacitance. So let's take a look at the next slide. We know that dielectrics are materials or insulating materials that contain molecular dipoles but no free charge. So let's think about what would happen if we insert a dielectric into a parallel plate capacitor. So we started off with this parallel plate capacitor, and it's got a strong electric field going from the positive plate to the negative plate. Now, first of all, why would we insert a dielectric? Sometimes we want to increase the capacitance of a system, which means it would increase the amount of energy stored. Now, if you want to increase the capacitance of a capacitor or a parallel plate capacitor, then one of the things we can do is take a look at the equation. C is equal to Q over V. We either increase the charge to increase capacitance, or we decrease potential to increase capacitance. So when we're taking a look at dielectrics, in order to reduce the potential, we have to be able to find a way to reduce the electric field between the parallel plates. Introducing a dielectric will allow us to do just that. So if we introduce a dielectric, it's going to reduce the amount of electric field in between the two plates, because for any given charge density on the surface of your parallel plate capacitors, the induced charges on your dielectric will help compensate or reduce the electric field within the parallel plate capacitor. So in other words, if I have a positive plate over here with a surface charge density of sigma, my dielectric that has been inserted into the parallel plate capacitor will have an induced negative charge on the left side touching this positive plate. And so this induced charge is going to reduce or cancel out some of the effects of the positive charges on this side. So that is what the dielectric will do. It will reduce the value of the electric field and thus the potential difference between the plates. And from that, it can increase the capacitance. Being able to explain this would be very useful. Now, how does it work exactly? If I insert a dielectric, first of all, a dielectric is made up of a bunch of molecular dipoles that are going to be manipulated within the presence of an electric field. Now, the parallel plate capacitor, which has a bunch of positive charges and negative charges on either end, will have a strong electric field. And in the presence of an electric field, these molecular dipoles will align with the negative ends towards the positive plate. So now that we have that, some of those electric fields generated by those dipoles are going to oppose the original electric field from the parallel plate capacitors and cancel some of it out. So the charge Q is going to stay the same, so the reduced field will reduce the potential and therefore give us a larger capacitance. And that capacitance is going to be proportional to some sort of constant multiplied by the original capacitance. And so we introduce the dielectric constant kappa. Now, the factor by which the field and potential difference decreases is called the dielectric constant. And so for a parallel plate capacitor with a dielectric, we can rewrite the equation for capacitance as follows. C is equal to some constant multiplied by the original capacitance, where this is the original capacitance and kappa is the dielectric constant. So this is all you would have to know when working with equations. You don't have to derive it. Now, for common dielectrics, we can have we can just list different materials and their dielectric constants to know which ones would help increase capacitance to what degree. So air is approximately 1, but you can use glass, 5.6, or you can use water, which is 80. So the dielectric constant of water is much higher than other materials over here, which means that it would most likely increase the capacitance a lot more than other dielectric materials. Next, we take a look at working voltage. It's another term that we should probably define moving forward. When you're talking about capacitors and capacitance, it's going to store a certain amount of energy and it's going to be proportional to a potential difference. So there is a maximum safe potential difference for a capacitor, which is called the working voltage. Anything that exceeds this is going to be at risk of what we call a dielectric breakdown. So going back here, we have a dielectric constant given for each of these dielectric materials, but also a breakdown field. And that breakdown field will basically give us that threshold we're looking for the working voltage. So in a parallel plate capacitor, the dielectric breakdown electric field is E equals to V over D. The smaller the spacing, the lower the allowed voltage before breakdown, the larger the capacitance, And the higher the voltage, the more expensive your capacitor will be. So just keep in mind, we use E equals to V over D to figure out what the working voltage is based off of what electric field thresholds we can have to maintain safety measures. Okay, so now we're going to take a look at a question or a sample question where a capacitor has a dielectric inserted into it. So we have a parallel plate capacitor with an area of 0.2 meters squared, and it's separated by a distance of 1 centimeter. And the 1 centimeter is simply going to be 0.01 meters. We connect the capacitor to a power supply and charge it to a potential difference of 3000 volts, then disconnect it. We insert a sheet of insulating plastic material between the plates that completely fills the space between them. The potential difference decreases to 1000 volts, and the charge of each plate remains constant. Find the original electric field, then the electric field after the dielectric is inserted, and then the dielectric constant. So there's 3 things we have to find here. So the first one, A, let's find the original electric field. So let's find E naught. Well, E naught, we know that the electric field is constant and uniform. So we can use V naught equals to E naught D immediately. E naught is equal to V naught over D, but we know V naught is 3000 volts, and we know D is 1 centimeter, and 1 centimeter is 0.01 meters. So we have E naught being equal to 3 times 10 to the 5 volts per meter. So that's our first answer. Now part B is asking for the electric field after a dielectric is inserted. So ED after dielectric insertion. Same thing. It's uniform. So that means ED is equal to VD over D. That D is actually a subscript. Let me just make that clear. The potential after the dielectric inserted is 1000 volts. The distance also hasn't changed. So that means ED is equal to 1 times 10 to the 5 volts per meter. And now we take a look at C. So I'm just going to move this down a little bit. We're trying to find the dielectric constant. And the dielectric constant is known as kappa. Just move this down further. Now here, there are 2 different ways of calculating it. The dielectric constant is how many factors the voltage or capacitance has changed by. So, option A versus option B. 2 different ways of solving it. Kappa is simply going to be V naught over VD. That's 3000 volts over 1000 volts. And that gives you a factor of 3. Option B, we have kappa is equal to CD over C naught. And we're going to have to try and calculate those. So why don't we go off to the side? C naught is equal to epsilon naught A over D. We know that this is 8.85 times 10 to the negative 12. Then you have 2 times 10 to the negative 1 meter squared. And then you have 1 times 10 to the negative 2 meters. And that gives you 177 picofarads. For CD, you have epsilon naught A over D. Actually, no, sorry. Don't want to do the same thing. We have to figure out how much it's actually changed. So we actually have Q over VD, another way to solve for it. Q doesn't change, so you end up with Q being equal to V naught, C naught, because C naught is equal to Q over V naught over VD, which is 1,000. V naught let's see, V naught is 3,000 volts. C naught is 177 picofarads, and then we have 1,000 volts. So CD is then equal to 531 picofarads. So between the two of them, you end up with 531 divided by 177 picofarads on the top and bottom, and you also end up with 3.00. So the dielectric constant, whichever way you choose to calculate it, will work. It's just a comparison between how many factors the voltage or capacitance has changed by. Now that we've taken a look at dielectrics in capacitors, and we've taken a look at how it affects capacitance, we can now move on to energy storage in capacitors. So how does all of this come into play when we're taking a look at how much energy a capacitor can hold? So first we have to take a look at electric fields within the capacitors, and then we can take a look at a term called electric energy density. It all starts by analyzing the movement of charge through a capacitor system. So we're going to analyze the movement of a small charge or a small differential charge element dq. We're going to move it from the negative plate of the parallel plate capacitor to the positive plate. And we're going to describe what happens and try to quantify this mathematically. So we know that a potential difference of V exists between the plates. So we know that for sure. We know that V is defined as some work per unit of charge. So because we have a small differential charge element, there's going to be a small differential work element associated with that movement of charge. So we have V equals to dW over dQ. And in fact, this V technically should be dV because it represents a small differential potential difference. Now we have dW equals to V dQ, and we have to move on to another equation to see if we can further analyze it. Now we have work, potential, charge. We haven't looked at capacitance, but we know capacitance is equal to Q over V. We have a Q and we have a V over here. So that means C is equal to dQ over dV. We can rearrange this to get dQ equals to C dV. Now, we have dQ here, and we have dQ over here, so this can replace the dQ here. So we have dW equals to VC dV. So if we want to get all of our work calculated, we integrate. So W is equal to the integral of dW, and we know dW is now equals to VC times dV. So we have the integral of CV dV. We can factor out the C, and we just have the integral of V dV. So once we have that, we have W equals to C times V squared over 2, and we end up with W equals to 1/2 CV squared. And that is the work required to charge a capacitor. If we're taking a look at the potential energy in a capacitor, then we just have to modify the equation slightly. The work that is required to charge a capacitor is equal to the total work done by the electric field on the charge when the capacitor discharges. So we define the potential energy of an uncharged capacitor to be 0, so that W is simply equal to U. Now, because W is equal to U, we can just say the potential energy stored in a capacitor is 1/2 CV squared. we know that capacitance is equal to Q over V, so there are various ways of representing this. You can replace the C with Q over V, and you end up with 1/2 QV. You can also replace the V with QC, in which case you get this. So since V is equal to Q over C, then you end up with being able to replace it in various different ways. So these three equations, you can just use them, whichever one is more convenient based on the question and the information provided to you. Now we take a look at the energy within the electric field. We keep talking about energy being stored in capacitors, and we should probably know where it's being stored. So if we look at the capacitor and we look at the uncharged version of the capacitor versus the charged version, we notice that the total charge is always going to be 0 because it starts off as conductors. So the only difference is really the arrangement of charge. So it's very important to understand that the arrangement of charge is where the capability of storing energy comes into play. So different charge distributions have different electric fields. So that means the energy is in the electric field. Because of that, we move on to describe something called an energy density within an electric field. Different electric field distributions will have different energy densities, which will then directly affect how much energy capacitors can store. So the amount of stored energy depends on the field and the different positions within that field. Energy density little u is the energy stored, capital U, per unit of volume. So unit of volume is the area times distance. So little u is equal to U over AD. We can represent U as CV squared over 2. We know that C is also equal to epsilon naught A over D. We know V is equal to ED. Combining all of this together and simplifying, we get epsilon naught E squared over 2, which is then defined as the electric energy density within a vacuum. So what is special about this equation? Although we derived the relationship for a parallel plate capacitor, this energy density equation will apply to any electric field configuration in vacuum. So when we're asking about where you can apply this equation, you can apply it to anything in a vacuum. But when we're talking about all the equations for capacitance in series and so on and so forth, they only work with parallel plate capacitors. So keep in mind that the electric field energy is electric potential energy. It's just a different interpretation of potential energy. And because of that, I want to go through two different views of this. The first view is that energy is shared between all charges. And then we take a look at potential energy within a capacitor. The second view, which is what the energy density equation is about, is when we consider energy to be a property of the electric field that the charges create. So it's this second view that allows us to create that equation for electric energy density and to apply it to any type of capacitor as long as it's in a vacuum. The next two questions have to take are taking a look at energy. First one's energy in a thunderstorm. A typical electric field in thunderstorm averages around 10 to the 5 volts per meter. Consider a cylindrical thundercloud with a height of 10 kilometers and a diameter of 20 kilometers. Assume a uniform electric field of 10 to the 5 volts per meter. Find the electric energy contained in this storm. So we are taking a look at electric fields and we're taking a look at energy within an electric field. So it means we should use the energy density. And so the proper equation to use would be UE for electric energy density is equal to 1/2 epsilon naught E squared. All the values are given to us. 8.85 times 10 to the negative 12 coulomb squared per meter, Newton meter. And then we have 1 times 10 to the 5 volts per meter. Whoops. And that actually has to be squared. Okay, so that gives us UE is equal to 4.4 times 10 to the negative 2 joules per meter cubed. Now next, from UE, you can find the total stored energy. So how can you do that? The energy density is the energy per unit volume. So UE is energy per unit volume. So basically, we would just have to multiply this by some sort of volume V to get the total energy. So total energy U is equal to UE times V. But we know that we're assuming a cylindrical thundercloud. So V is going to be equal to pi r squared h, where r is equal to 10 kilometers because the diameter is 20 kilometers and you have a height of 10 kilometers. So U is then equal to 4.4 times 10 to the negative 2 joules per meter cubed. Then you have pi r squared h. Like that. And you end up with 1.39 times 10 to the 11 joules. And that is your answer for problem 6. In problem 7, we want to take a look at what happens to a shrinking sphere. A sphere of radius r1 carries a charge of q distributed uniformly over its surface. How much work does it take to compress the sphere to a smaller radius of r2? Now, this is a little bit more complicated, and we're first going to draw a diagram to help with this. Keep in mind, we're still in the energy unit, so we're going to have to think of energy. So, in that case, we have to figure out how to compare the two spheres. The first sphere, I'll just draw like this. We're going to call this R1. And it's got a bunch of charges Q around it. So charge Q. Let's make we'll use green for the electric field lines. I'm going to call this E1. Now, what happens after? We're going to shrink it, and we end up with a much smaller, smaller sphere. And now we have a radius of R2. And the charge density is probably going to be more condensed, but we still have that charge there. So in blue, I'm going to draw the new electric field lines. We're going to call this E2. And in purple, I'm just going to briefly draw out the original size of the shape. So that's how much it's shrunk. So when we're taking a look at how much work was done, we have to explain that the work done should be the difference in energy between the two electric fields. So we know that the field is going to vary with position. So that means U is equal to 1/2 epsilon naught integral of E squared dV. So with R2 being small, we assume it looks like a point charge. So that means E is equal to KQ over R squared. And we know dV is equal to 4 pi R squared dr, which is a volume of a thin spherical shell. So to find U, all we have to do is derive from R2 to R1, or R1 to R2. U is equal to 1/2 epsilon naught integral R2 to R1 of KQ over R squared 4 pi R squared dr. Now we can think of things to factor out. We end up with KQ squared over 2 because we have K squared, Q squared, and then 4 pi that's factored out. And we also know that epsilon naught is equal to 1 over 4 pi K. So that helps us in reducing this to a more manageable number of variables. We have integral of R2 to R1 of R to the -2 dr. Then simply we would have KQ squared over 2, and we get 1 over R, or -1 over R as our integral. So we have 1 over R2 minus 1 over R1, which is equal to work. And that will be the amount of work done to compress the sphere to a smaller radius of R2. So we're finally able to move on to applications to life and medical physics. So where can capacitance be applied to in things that we commonly see or things that we can use for medicine? The first thing I want to start with is cell membrane capacitance, because I want to start small. We can start with biophysical modeling and then move on to the macroscopic scale, where we're looking at biosensing and touch screens, and then of course to medical applications like defibrillators. So let's start off with modeling the cell membrane. So in this slide, it's a slide that I usually present for Physics 380 when I teach it, because we actually go through the different types of ways to model a cell membrane. But you'll see through this diagram that one of the options is to model the cell membrane as an RC circuit. Now, we won't really go into detail with all of the components of this RC circuit, but just looking at the cell membrane itself, we can assume that it's a parallel plate capacitor, because it kind of looks like one too. So you can assume one side's positive and the other side is negative, even though that's not exactly accurate. That's why over here, when we're modeling, maybe only this domain or this portion is positive on one end and negative on the other, and maybe this region is flipped. So we're keeping it simple. What happens when we consider a cell membrane as a capacitor? So lipid bilayers of cell membranes can be electrically modeled as a parallel plate capacitor. Conductors are going to be on the plane of the polar lipid heads where all the charges will reside. The dielectric layer is then going to be the hydrocarbon tails. So we have a separation between the polar heads at distance of A. We can assume one side of the cell membrane is positively charged and the other side is negatively charged. The specific capacitance, which is the capacitance per unit area of cellular membranes, was determined in the 1920s, had a value of approximately 1 microfarad per centimeter squared. and the dielectric constant was derived to be 3 due to the knowledge that cell membranes have lipids, or technically oils, which regularly had a value of approximately 3. And because of all these known values, they were able to measure the capacitance per area of a cell membrane. So why is this useful at all? Sometimes it's used to estimate the thickness of a cell membrane using parallel plate relations for capacitance. But is it actually accurate? If you do the calculations, you'll find that the membrane will have a thickness of approximately 3 nanometers. But in reality, membranes are 6 to 8 nanometers thick with an average of 7.5 nanometers. So our guess was like 50% correct, or 50% of the correct value. It's still a good attempt, and it's still plausible because shorter lipids could have smaller membrane distances. So based on the specific capacitance that was determined in the 1920s, it's not 100% accurate, but it's enough to give us a good estimate. So then we go on to looking at how much charge resides on a membrane. So we have to make a few assumptions. We're going to assume that the charge on a cell membrane is uniformly distributed. In reality, definitely not the case. We can estimate the charge on the membrane if we make this assumption. So we're going to assume V is equal to 0.1 volts and that the specific capacitance is 1 microfarad per centimeter squared. Using these known values with Q equals to CV, we can have 0.1 microcoulombs per centimeter squared. And then we take a look at X. Now, if X is the distance, if X is equal to the average separation between charges on the membrane surface, then we can assume that there is going to be 1 charge per surface area of X squared. So we can calculate the number of charges per centimeter squared. If we assume 1 charge per X squared centimeter squared, then we can use this value divided by the distance here. We have 1.6 times 10 to the negative 19 coulombs, and we have 6.25 times 10 to the 11 charges per centimeter squared. And with that, we can find that there is about 1 charge every 13 nanometers in a square array over the surface of the membrane. We can also calculate the electric field inside the membrane in that case. Now, this slide is purely just meant to be an overview of how one would start modeling. And so when you start modeling, you have to make assumptions. And in this case, we've made the most simple assumption, which is already a bad start because cell membranes are not uniformly distributed. So the value we get here is truly an approximation based on an oversimplification. So this is probably not very true, but it gives you a sense of what steps are required to be able to get this number. Next, we take a look at biosensing and touchscreens. So capacitive sensing or capacitance sensing is a technology commonly used in electrical engineering. It allows us to detect and measure anything that conducts electricity, and it also detects anything that has a different dielectric than air. So when we're talking about biosensors or any type of sensor, it can involve proximity, it can involve pressure, it can involve position and displacement, the application of force to a specific location, humidity, acceleration, fluid levels, anything. So based on capacitive coupling, the transfer, So capacitance sensing is really based on capacitive coupling, which is the transfer of energy within an electrical network. So when we're talking about sensors, especially touchscreens, we can use our hands or our fingers because the human body is an electrical conductor, or at least some sort of dielectric. We can have charge. So for sensors, the parameter that is sensed is going to cause a change in the capacitance in the area that has sensed this element. The screen's firmware will then recognize the change in capacitance and result in a response to the stimulus. So let's take a look at how that happens. When we're looking at human interface devices, we take a look at touchscreens because that's something that everybody uses nowadays. We use them for computers, for mobile devices, games, even learning. So a touchscreen panel consists of an insulator, like glass, that's coated with a transparent conductor, like indium tin oxide, commonly abbreviated to ITO. Our human bodies are electrical conductors, so when we touch the surface, it results in a distortion of the screen's electrostatic field. And the software is going to monitor that change and then convert it to a location for the software or the program to understand where that touch was located and to open up that app or program. So a change in capacitance is then measured at the location. So let's take a closer look at these touchscreens and how they can sense touch, because there are two different types that you will have to differentiate between. So the two different types are resistive versus capacitive touchscreens. And just by the name of these touchscreens, you should be able to figure out what they refer to. Now, we have all used touchscreens before. You've probably used some where you have to really poke the screen and push into the screen, so the screen actually sinks down and then something happens. This is called a resistive touchscreen, and it consists of thin layers. So this is an example of a resistive touch screen. If you're pressing down on the touch panel, it's going to bend the top layer to make contact with the bottom layer. What's unique about this is that the top layer, so the red part over here, it's going to be a transparent electrode film, and the bottom also has another flat film. The top layer is separated by some sort of spacer, and in between the spacers you can push down, and the conductor or the transparent electrode film in the top touches the one at the bottom, and a circuit is closed so that a touch is sensed. So when the circuit is closed, it causes a current loop to register a touch. When we're taking a look at capacitance touch screens, they consist of two layers: the surface insulator and the conductive layer behind it. So when you're touching the surface insulator, a parallel plate is going to be created and the electric field is distorted, which registers as a touch. So where are both of these used? When we're taking a look at resistive touch screens that consist of multiple layers, when someone presses the touch panel, it's going to sink down and cause a closure in the current loop. These resistive touch screens can generally only be used for a single touch device, kind of like buttons, because they cost much less to make. And they also incorporate into your application and respond to any type of touch. So you can use your finger, you can use a stylus, you can even use any hard object to just push it. So what I would say is that if you're choosing between a resistive and a capacitive touch screen, a resistive touch screen is more effective for simple panel controls like the GPS control panel in a car, other keypad replacement applications, or in applications where you have to use a glove. Now, if you want to have a touch screen that senses actual human touch based on location, then a capacitive one would make more sense. So capacitive touchscreens are commonly made of two layers. You have a surface insulator and then a transparent conductive layer behind it. The human body itself is an electrical conductor, so when the touch panel is touched by your finger or a conductive pen, the electrostatic field over here is distorted. So you can see over here there's a distortion that's sensed by the program. It then will send an instruction to the rest of the system to register a touch at this location. So it converts the distortion of the electric field into a pinpoint location. Now, because of this, capacitive touchscreens are capable of multi-touch controls, and they require less physical force to register a touch. So if I have a finger poking the screen over here, it causes a distortion. If I use two fingers, then it causes 2 peaks to be created, and you get 2 pinpoint locations of electrical field distortion. If you use 3, then you have a greater magnitude within these 3 areas. So when we're looking at mobile devices where you have a single touch for one sort of application, a double touch for something else, or a triple touch, then these are things that are possible if you use a capacitive touchscreen and the electric field is distorted. Now, comparing capacitive touchscreens to resistive touchscreens, it seems more plausible that capacitive touchscreens are sturdier and they're going to be longer lasting because you don't have to push and bend a film. You just have to distort the electric field over and over again, and that's really just a software issue. So they are longer lived, and so they're more suitable for high-grade panel controls or mobile phones, which require regular use. So here's another diagram of the capacitive touchscreen and essentially the parallel plate capacitor that's created. So over here, the whole system is grounded and you have some sort of capacitance from your sensor. Now, our bodies are electrical conductors as well, and we're also grounded, and we also have some sort of capacitance. So when we're touching the screen with our fingers, then there's also a finger capacitance that has to be considered. And that means that we have a capacitance from the sensor, a capacitance from the finger. When that touch takes place, we form a parallel plate capacitor system in series. And that's how we can calculate a difference when we make that touch on the screen. Okay, so let's move on to defibrillators. We commonly think of defibrillators as medical devices that help save lives when we need to deliver an electric shock to the human body to treat life-threatening cardiac arrhythmias or like heart attacks. So healthcare professionals regularly do use defibrillators to treat cardiac dysrhythmias. They really do require a huge dose of electric current to be delivered to the heart to jumpstart it. And we have to ask ourselves, where does this energy come from and where is it stored? And the simple answer is it's stored in a giant capacitor. Defibrillators need a huge charge to be stored. And so that means we have to find ways of being able to increase the capacitance and store more energy within that defibrillator. So the equation for capacitance is epsilon naught A over D. It means you can either reduce the separation distance or you can increase the surface area of your capacitors. So obviously there is a limitation to size because we can't create an unlimited size defibrillator. So the only thing we can do is increase surface area by rolling the capacitors. And by rolling, I mean something like this, where you end up with a parallel plate, but it's just rolled within each other so that you can create that, that larger surface area. So this, in effect, will increase the capacitance. And keep in mind, this is just an overall drawing of how the configuration can look. It actually doesn't look like this exactly, but just so that you can visualize the process of rolling a capacitor to increase the capacitance, that's how you would visualize it. But even if we increase the surface area and we decrease the separation distance, how do we charge the capacitor? It's actually quite complicated. The charging system involves a variety of voltages and also deals with direct current, DC, and alternating current, AC. Should be changed to AC. The voltage required is about 2000 volts, so that's a huge amount of potential. And a step-up transformer is going to increase the voltage that comes into it. So the device is going to convert an AC current from the transformer to a DC current, which is then delivered to the capacitor for charging and then delivered to the patient to give them that electric shock. So in other words, defibrillators are constantly used as defibrillators constantly use a capacitor to store a preset quantity of electrical charge that's rapidly delivered as direct current to the patient. So it makes sense that depending on what kind of arrhythmia the patient has, there's going to be different set charges to target different types of arrhythmia. So now we have a few questions to look at. What does this large shock do? Why do we rub the paddles together before applying the shock? Is it even required? And why do people shout clear before applying a shock? So let's answer these questions through a discussion. In a defibrillator, the delivery of a large charge in a short burst to a set of paddles across a person's chest can be a lifesaver. So the person's heart attack may have arisen from the onset of a fast, irregular heartbeat, either cardiac or ventricular fibrillation. The application of a large shock of electrical energy can actually just terminate the arrhythmia and allow the body's natural pacemaker, to resume normal patterns. So it's almost like restarting or jump-starting a system. Now, another common question is why the two paddles of a defibrillator need to be rubbed together before applying the electrical shock. Now, it's not really that it has to. It's because you usually coat the panels or the paddles with a conductive gel, which helps to conduct the shock from the paddles to the skin. Rubbing the gel onto the paddles with your hands is going to take a really long time, so it's usually easier to have the two paddles and rub them against each other to spread the gel more evenly and more quickly. Now, something to consider is whether it's even required nowadays. We have definitely improved in recent decades with defibrillators. This is what you see in movies with the two paddles and the shock. In real life, modern defibrillators use flexible pads that are pre-coated with a conductive gel. So you basically rip off the coating, you stick it on the person's chest at specified locations, and it already works. So you don't need to rub two pads together. And if you have a mobile cart with a defibrillator, like at the hospital, an older device would most likely have the two paddles. But now if you're using an AED or just a carried defibrillator device, then it will have those pre-coated conductive gel adhesives that can stick onto the person's chest so that you don't have to spread the gel yourself. So you just stick it onto the patient, do your thing, and so the rubbing of the gel pads has become quite obsolete due to modern advancements. Now, last question. In movies, we always see somebody shout clear before they deliver the shock, and is that true? And is that required? And yes, it is true and required because the human body is conductive. So if you're touching the person who's receiving the shock, it makes sense that you're probably going to receive the shock as well, and you'll probably end up lying on the floor with them after the shock is delivered. So it would be wise to let everybody know when you're delivering the shock. Don't have to shout clear, but you can let them know that you're delivering the shock and make sure nobody else is touching the patient when that shock is delivered. Now for a summary. What are some key concepts and what are the important equations from this chapter? So I'm just going to go through the key equations because the concepts were covered primarily throughout the whole chapter in the last slide, as well as through applications. They were summaries themselves. So for equations, remember the equations for capacitance and that there is equivalent capacitance in parallel and series. These are the equations that you can use whenever you want. When we introduce dielectrics, you have capacitance with a dielectric, kappa. We can calculate the work required to charge a capacitor, which is equivalent to the potential energy stored in a capacitor, which can be written in 3 different ways. And of course, this gets its own slide because the electric energy density in a vacuum applies to all different sorts of capacitor systems. And because it provides us with a different view of electric energy, it's the fact that we view it as the electric field having a certain amount of electric energy versus an object having a certain amount of potential. So if we ever want to calculate the total electric energy stored within a certain volume, we can always integrate it that's pretty much it for this chapter. Next, we're going to move on to additional systems and circuitry.